So hello everyone and welcome to the session. I'm Niklas from CrateDB, and today we will talk about resilient data streaming with CrateDB as a database for real-time analytics. So the scenario that we want to look at today is a typical real-time ingestion data flow. So this means that we have a set of data producers, and this can be either physical devices like sensors, for example, that produce data, or if you are more into digital products, then it could also be users interacting with your platform, with your software tools, and leaving traces about how they use your product. And in both of these cases, typically these data producers ingest their data into a message queue. In our case, we assume it is Kafka. And then there is a consumer that reads from the message queue and inserts that data into some sort of persistent data store. And in our case, we work here with the Node-RED as a low-code tool that's very easy to use if you want to just retrieve rows from a message queue and then forward it into a database such as CrateDB to then have real-time analytical insights into how the data performs. And so these chains, these pipelines typically work great if everything is smooth, everything is operational. But what we want to try out today in this session is what happens if one of the components actually fails. So what do we need to consider for resiliency, for high availability? And this is, of course, a question that we need to ask for all the different components here involved in such a pipeline. But since we are here from CrateDB and we concentrate on the database aspect, we are going to actually try out live now how resiliency, how the failure of a node in CrateDB as a distributed database, how that affects the pipeline as a whole. All right, so let's switch over to a local CrateDB installation that I have running here on my machine. So what's important to understand is that CrateDB is really built as a distributed system. So typically for a productive use case, we always have 3 or more nodes running, which you can see here in this header line that I have a setup of 3 nodes. And why 3 nodes? We would see that during our exercise, but let's take first a look at the data that we have. And to keep it simple, we have just one single table here, a payments table. You can see the number of records keeps increasing. There is active ingestion at the moment happening from Node-RED that receives messages from Kafka. We can take a quick look at the actual data, which is typical time series data. So we have a timestamp from when the record arrived, and then a couple of attributes. The data itself is actually, for our case right now, not that much of significance. It could also be a different type of data. I think the most important part here is that it's basically time series data where continuously new records arrive and the table keeps increasing in size. Now, what's a bit more relevant for the high availability and the resiliency is what we can see here for the number of shards. So as a distributed database, CrateDB has the concept of sharding. So this means that this one payments table that we have here is, in our case, split into 3 equal shards. So this means that basically 1/3 of the rows goes into each of the shards, and then these shards are distributed across our 3 nodes. So you can imagine this basically as then every node having one shard with then each 1/3 of the data. So this way we can achieve that every node is participating somehow in storing and processing that data. And so the sharding is already very important for parallel query processing and for high performance. But if we want to talk now about resiliency, then what is important is the replicas that you see here in that additional field. We set it here to 0 to 1. So this means that the cluster tries to allocate up to one replica. And this is also why you see here that in total, we have 6 shards. So for these 3 primary shards that I just mentioned, we now create basically an exact copy of those 3, which makes it then 6 shards. And to make it maybe a bit easier to understand, we have here a visualization that shows us on these 3 different CrateDB nodes where these shards are located and how primary and replica shards are connected. So we have shards 0, 1, and 2. And if we hover here, for example, over shard number 0, then we see there is that bright green color here at the bottom. This is the primary shard, which happens to be on node number 1 at the moment. And then there is the replica shard here on top, which is on node number 2. So this is very dynamic. It can basically change as the cluster also changes. But what is important to note here is that CrateDB automatically takes care that primary and replica shards are always on different nodes. So if we check for shard number 1, then we see the primary shard is on node number 2, the replica shard is on node number 3, and similarly for shard number 2, it's also located on 2 different nodes. So this is a very important prerequisite for the event that we now want to look at, which is what happens if really one of the nodes disappears from the cluster. And here we need to differentiate between 2 different scenarios. So a node disappearing could have different reasons why it happens. It could be anticipated, it could be planned, or it could be unscheduled and basically be a consequence of a failure. The first scenario, let's really look at what happens if we anticipate that the node is going to become unavailable. So a typical reason why that could be is if you run some sort of maintenance, so if you want to upgrade the underlying infrastructure, or also if you want to upgrade the CrateDB version, then you might know ahead of time that you're about to do a restart of the individual nodes, which we would typically do in a rolling fashion, so one node at a time. And what we want to monitor now is, and here I'm switching over to a Grafana dashboard, which plots us the number of records that get inserted into that table at the moment on a per second basis. And I have a script running in the background that inserts data into the Kafka queue, and it's inserting one record approximately every 100 milliseconds. So what we can see here is basically we have per second 9 to 10 records. So more or less exactly every 100 milliseconds, there is a row arriving in the database. Ignore the most current reading here because that second is still ongoing. That's why it's a bit lower. But we see here that there is a pretty steady, pretty equal flow of data. So this is what we typically want to see in those message queue scenarios, that the database is always keeping up to the ingestion. And so what we want to do now is I'm running it here on Docker, the setup. So every CrateDB node is a separate container. And we will now take node number 3 and just click the stop button here. So the stop button in this case is like a graceful shutdown. So it sends the process in the container a termination signal, and then the container still has the chance to basically send a command to the other CrateDB node saying, I will shut down in a couple of milliseconds, be aware I'm leaving the cluster, and then CrateDB can take some steps to basically gracefully handle that scenario. So let's do this. Click stop, and then observe what happens here with the primary and replica shards. I'm clicking stop now. And what you can see here is node number 3 has disappeared from the list. And at this point in time, the primary shards are all still present. The location might have changed. So if there was any primary shard on that node number 3 that is no longer there now, then because it's a graceful shutdown, CrateDB would basically switch the role of a previously replica shard to be the new primary shard, so that if that node leaves, the primary shards are all covered, and you can just continue ingesting data and also read data. The only thing that we are missing now is the replica shards. So you see now we have replica shards that happen to be on node number 2, and we lost some replicas because we made them new primaries now. And what happens now is basically CrateDB waits for, think about half a minute to see if the node will come back. Because especially for the scheduled maintenance operations, if you take a node down and I'm just going to run an upgrade, it's going to come back in a couple of seconds, then you don't want to start data movement to compensate for missing shards. That's why there is a grace period. And you saw now that the replica shard number 1 and number 2 were recreated about half a minute later, roughly, to restore the full state of primary and replica shards. So this is very important in case now yet another node would potentially fail and leave the cluster. In such a situation, we want to be fully restored with the primary and replica shards present. And let's now take a look at our Grafana monitoring here. Did that have any impact on our ingestion pipeline? We still see 9 to 10 rows coming in and being processed per second. There is a slight deviation here to down to 8 seconds. Not even sure if that is related exactly to what we are doing. Might be, might not be, but you see basically it's a neglectable deviation. We see still a very smooth and very equal processing of events. Now, the only thing we need to consider now is, of course, that the load that previously was shared by 3 nodes now needs to be compensated by 2 nodes. This is something to consider when scaling or sizing your CrateDB cluster, to make sure that you can actually compensate the failure or the temporarily unavailability of a node from a hardware resource perspective. Okay, so everything happened quite smoothly. So let's power that node back on. So assume our maintenance operations have completed. We click start here. Now the node basically still has on its disk information of the cluster. So it will now, after it started, reconnect to the other nodes in the cluster. You can see here now node number 3 is back. It then checks for the state of the cluster and would see if the data that it has stored locally from the point in time when it left the cluster, if that is the current. And because we have data continuously coming in, of course, the data that was stored on that node is slightly outdated now. So that node will then check, okay, how big is the delta? If it's small, then it will just ask the other shards to basically send over the delta. So it's then up to speed again and up to date. Or if it happens to notice that the data is very significant, then it might also decide just to discard the local copy of the data and basically start fresh by creating a completely new copy of the data. And you can see here now CrateDB put again 2 shards on that node number 3. So it's back again at participating in the cluster state and serving queries. And taking a brief look at our ingestion pipeline, pretty much as expected, because we actually added capacity to the cluster. Everything is still fully operational, fully running. We don't see any impact at all here in our throughput. But now, more interestingly, let's really look at the scenario of what happens if we cannot anticipate that this node number 3 has a problem. And for this, we can use here the pause feature in Docker, because this is really, the moment I click on that button, it's basically going to freeze the container. So it's going to stop reacting to any messages over the network from the other nodes. So this is really as if I would basically unplug the network cable, and all of a sudden it just couldn't communicate anymore. It can't send a heads up to the other nodes. So this is simulating really a non-graceful removal of the cluster of the node. So let's try. Click pause here and see what happens. And immediately we see, okay, node number 3 still shows up here, and CrateDB has a number of checks basically that it performs to verify if the nodes are still there, if the nodes are operational. So what's going to happen now is Node-RED still sends insert commands to the database, to CrateDB. And CrateDB will always wait for both the primary and the replica shard to acknowledge that the data has been written. And in this case, now node number 3 will not acknowledge the writes anymore. So CrateDB will wait for a certain amount of time and then basically reject the write statements and send it back to the client, to Node-RED in this case, saying your query failed, it was not acknowledged. And then after a certain period of time, if the node keeps to be unresponsive, then the other 2 still operational nodes will actually remove the node from the cluster and just continue operating on their own with just a set of 2 nodes here. And this is also, if you just watched what happened here or what happened, the node number 3 still showed up for some time. And then it was basically removed if there were any primary shards on that node. Those would be promoted here to the other nodes, and we could also see again same picture as before with the graceful shutdown. Replica shards are missing, they get recreated, and now we are back to our original state. And let's look now at our monitoring, and here we see now this very classical shark fin pattern. So everything still went fine until here 11:41:39 roughly, and that was probably the point where I clicked the pause button. And then there is, of course, a certain period of time until CrateDB has recognized that the node is unavailable. So you do want to actually wait for some time, because if there is just a period of high network latency or high network traffic, you don't want to be premature in basically declaring a node non-operational, because otherwise your cluster might become flaky and you still want to have it in a stable state. And then the application, so Node-RED, was basically queuing the inserts that happened, that were generated in the message queue from the producers. And then basically once CrateDB was fully operational again, once it basically settled with the 2 nodes that it has, and then accepted inserts again, then that's why you can see this peak here of 100 rows per second. So how long did it take? 41:40 to 42:11. So it's basically half a minute roughly that it takes for CrateDB to become operational again. And then once that peak, these messages that have buffered on Node-RED have been processed, now we are all the way back to our regular 9 to 10 messages that get processed here per second. And now again, we have a fully operational cluster, one node less, but other than that, it continues operating. So let's power the node back on. And I mean, this, we already know what happens. We have seen it before. This is now no different from the previous scenario. The node comes back, the node checks, okay, is my data still current? Most likely not. It will allocate some shards from the other nodes, and then it makes sure they are synchronized and gather any additional data that they might have missed. All right, and this basically already concludes our small demo here on how CrateDB handles high availability in a distributed setup. Let's take a brief look at the takeaways that we can get from this small exercise. So first of all, what's important in such a scenario is that you have some buffer when you do the capacity planning. So if you have 3 nodes and you ask yourself the question, okay, how much memory should I have? How many CPUs should I have? Don't size your nodes to be then with your typical production node already at 90% CPU usage, let's say, because then it might be very tough if one node becomes unavailable for the other nodes then to compensate. So always leave a bit of room for such scenarios. Then the number of nodes that you have, the absolute number of nodes, also has a direct impact on how visible such failure scenarios could be. So in our case, with 3 nodes, if one node fails, we basically lose 1/3 of our capacity. But imagine if we had a 10-node CrateDB cluster and one node fails, then it's just 1/10 of the full capacity. And maybe not even all tables would be impacted by it. So if you ask yourself the question, should I have few nodes, but maybe with lots of compute power, or should I have maybe more nodes, but every individual node being a bit smaller with less compute power, then this aspect will actually favor the scenario where you have more nodes, so that if one node fails, the impact will be contained. Then looking a bit ahead of this very simple example, you should definitely also think ahead, what type of failure scenarios do you anticipate in your production scenario? So we now, for the simple demo, had every container running on the same machine, but typically you might have your containers distributed across different availability zones, across different data centers, across different racks. So really think about what is the scenario that could happen, what facility, what entity could become unavailable, and to which of these scenarios do I want to be insured against, so to say, by having proper redundancy. So this is definitely something to plan, as this will also tell you how much redundancy you actually need. And then the last item here, a bit similar in that direction, is to also anticipate the unavailability of the database in your toolings, in your applications. So it's very important is, even if it's a distributed system that is highly available by nature, by architecture, still consider that there are these small time windows where the database might not be able to process data. Where in our case with Node-RED as the consumer from the message queue, it's important to also there have some queuing so it can buffer messages, actually wait for the database to be available again, and then basically process everything that is queued. And in a similar way also, it needs to be able to gracefully handle error messages. So if the database really returns an error saying I cannot process this insert statement at the moment, then this needs to actually go into a queue, or on the other side, if it's more on the analytical application side, then you might also want to consider really retrying and only reporting an error to the user or aborting some process after a certain number of failures when you can actually assume that you won't be able to recover from a given error in a certain period of time. Great. So this then concludes our session here. I hope you found it interesting to think a bit about high availability and what happens if things really go wrong. If you want to learn more about real-time analytics insights and discuss the nitty-gritty details of designing a system that is available and that can handle all these different scenarios, then please talk to us. I'm happy to meet you. Thank you and goodbye.